So for this tutorial we're going to be looking at grouping. This isn't a very exciting subject, but unfortunately it's very important, so I'll try and get through it as quickly and painlessly as possible. The reason it's so important is that almost every node has a group option, and they're a very powerful way of sorting out your geometry. So let's start by dropping down a geometry node and placing a grid. There are a couple of different ways that you can manually add components to a group. So first of all, we can use the select tool and simply pick out components. See here we've got primitives on, but we could also select points or edges or vertices. So let's select some primitives. You can shift select, you can hold down Alt to remove your selection, and you can drag select as well. Now to add these to a group node, we use the tab key and type in group. Now something you need to be careful with here is that you need to have your cursor over the viewport, otherwise it'll just drop down an empty group node. If we type in group, now you'll see it's attached to group node and it's created a list of all the numbers for all the primitives that are part of that group, and it's assigned it a name. You see we're a primitive group. We could change it to points and it will take points instead, but we want primitives. Let's call this group manual. Now something that's quite interesting about a group, which isn't immediately obvious, is that groups and attributes are the same thing. So if we look inside our geometry spreadsheet and look at our primitives, you'll see that we have a group called manual, and everything inside that group has a value of 0 or 1. So all making a group is doing really is creating an attribute that uses a 0 or a 1 to say whether each component belongs to that group. So when you look at it that way, it's quite simple, and you can perform the same things on groups as you can on attributes. Manually selecting components is only one of the ways you can create a group, and if you're working procedurally you'll probably almost never use this. If we have a look, there are simply in the group node a collection of different ways of creating groups, and there are some variations on the group node as well that we'll look at. So I'm going to create a chessboard and place some chess pieces on it, and this is going to show us hopefully as many as possible ways that we can create groups. So first of all, we're going to create a box, as we want a 3D chessboard, and we're going to make it 8 by 8 squares across, and we're going to add 9 divisions, which should give us 8 squares. 1, 2, 3, 4. We need to make it a polygon mesh, that's why it's not behaving as expected. So let's go back to our 9 divisions. And that looks like it's correct. So now we have each square the size of 1 unit on the grid. Now let's make our first group selection. So this time I'm going to put the group node down first, because we're going to create a procedural group. Now with our chessboard we only want to work on the faces that are pointing upwards. So first of all we want to make a group of all the upward pointing faces, and we can do this by normals. Check that our group type is primitives, and we want the normals that point in the 0, 1 0 direction. So that's 0 in X, 0 in Z, and 1 pointing upwards in Y. The spread angle will actually select everything because it's 180 degrees. So we'll make that less until we've only got the top faces. So there we go. We could make it 0, but we might at some point want our faces to be a little bit uneven, as if the chessboard was made out of wood that wasn't quite perfect. So we'll keep that angle above 0 just to make sure it gets everything pointing in roughly that direction. Next we want a group that just consists of the black squares. Now there's a problem here. So there's a couple of ways I could do this. I can add another group node. And if we open up the help with group node, it will give us some syntax which allows you to write some simple expressions to select different types of components. Annoyingly, this syntax is not the same as the vex syntax or the expression syntax, so you're just going to have to take a look. I don't think we've got the right thing here. Let's just do a search for group. No. Groups and geometry, that's one. So this is a more general overview of grouping, and it has a list here of the group syntax. I'll put a link to this below the video as well, so you know where to look for it. So this group syntax is used in the base group. So if we have that enabled, in fact the default is exactly the same as using a star, which just selects everything. We can, as you've seen already, put a list of values of component. So let's say to 10. Oops. So now we'll just take the first 10 components. The order that it selects them is the order of the component numbers. So you can see that to get 0 to 9. Yep. In fact 0 to 10. So if we find out the total number, so we have, I think we have 151 here. Yeah, so that's, nope, 159. So now we can use a step so it doesn't select every component. So now it takes every second component. And now you see the problem that we have with the chessboard, because we want our components to alternate on the different rows. So I'm going to look at a different way of doing this. There's another node which is called group by range. This is a more manual, and certainly when you're getting started, probably a simpler way of selecting ranges. You can do everything that you can do in group by range here using the group syntax, but group by range makes it possibly a bit easier. So the default is to give you a number relative to the start and the end. So we can make that any number you want. So that just eliminates them from the start, and this will eliminate them from the end. So you see it's starting to rule them out. And then you can filter them out. So if we were to put 1 of 2, we get exactly the same result. I spent quite a lot of time trying to figure out a nice neat solution to this and couldn't come up with one. The best that I could come up with, short of selecting the grid points manually, is to create it on a separate object and then transfer the group across, which we'll show you about the group transfer node, so we're going to set it up that way. So now I'm going to create a grid, and this time I'm going to make an uneven number of columns. So we're going to make 9 columns, so we'll make it 9 units across, and we'll keep our rows on 10, and then we want to offset it slightly, so it should sit exactly on the other, so on the surface of the grid, because we want it to be touching, because we're going to transfer based on its position, and we want to offset it also in the X and Z direction so that it lines up. You'll see why I'm doing this in a minute. Now we're going to attach our group range to the grid node, and now you can see we're getting exactly what we want. We're getting a chessboard pattern. That's because there's an uneven number of squares in each row, so it starts each new row with a different colour. Now if we put these two next to each other, you'll see that the squares exactly match up, so we can transfer the group based on its position. So for this we want a group transfer node, and we want the geometry that we're transferring to be our box, and the geometry we're transferring from to be our group range. Now let's call this group black, because this is the black squares, and we want to transfer a primitive group called black. You'll see that any groups that exist on the object that's being input are available for you to use, which, apart from anything else, saves typo errors that can be hard to track down. Now we've got a distance threshold of 10, which is much higher than we want. If we look at the geometry spreadsheet, we've got our black group, and it's actually transferring a lot of them across. It's not very obvious to us where our group is, so a handy trick if you're wanting to visualize groups is to stick in a blast node delete non-selected and put in your group. So now it's removing everything apart from that group, and it's quite easy to see where it is. So if we go back to the group transfer, we want our distance threshold to be much lower, because we only want the faces that are actually touching each other to transfer. 0 is perhaps a little too low because it's bringing in some errors, so let's make 0.01. So now we have our black squares. Another way you can visualize this is colour, which is what we're going to do to it now. So let's make a black colour node, hook this up, and only input the black squares. And we will need to add this to primitives, not points. So now we have something that's starting to look a little bit like a chessboard. We probably want our chessboard to use Z as its depth, because that conforms to the way 3D works. And a chessboard always has a black square in the back bottom left corner, so we want to tweak this a little bit. We offset by 1, and that will cycle all the squares round by 1, and now we have our black square in the correct place. Let's clean up some of these nodes that we don't need anymore. So the next thing we want to do is give our chessboard a border, and to do this we want to select the edges. Now there's a few ways we can do this. We can, let's put down another group node. So we can select it by normals again, but it's a bit more complicated this time because we want the faces that are facing in 4 different directions. So we could select by normals 4 different times and combine those 4 groups, or we could select the upward facing and downward facing, so that's 2 groups, and then a group of everything and subtract up and down from that. But there's a simpler way to do that, which is to select within a bounding box. So we want our bounding box to encompass nearly, but not quite, all of the chessboard. So you can see it's just a little bit smaller. If we wanted to do this completely procedurally, we could get the size of the box from the input and tie it to this size and make this one a little bit smaller. So at the moment it's only selecting faces that are completely contained within that bounding box, but we can turn on partially occluded entities, which will give us the opposite of what we want. Now, in order to get the inverse of this group, we need a group of everything. So first of all, let's call this top bottom group, and now we'll make a second group. It's very tempting when you're making collections of groups to put them side by side, but in fact a group, apart from creating a group doesn't change your object in any way. So you want each one to go into the next one, and then you're just building up a collection of groups without actually changing your object. So this group, we want everything. If you want to remind yourself that that's what you've done, you could put a star in there, but just doing nothing will give you a group of everything. Let's call this all prims. And then finally we want a group that consists of all our prims, but not the top and bottom. So here we want a node called group combine. And this is similar to a Boolean. We're just performing operations that combine or eliminate or subtract different groups from each other. So the way you would set this up is, this is the name of our new group. We'll call this edges. And the new group is equal to the group that we made called all prims, which is everything. And then we want to subtract our group top bottom. So you see we've eliminated the top and the bottom now, and we're left with just the edges. And now that we have that group, we can extrude it to make a nice little rim. Use poly extrude because we're working with polygons. And we want to use, yes, we have got a group called edges. We want to use a new group called edges. So now you can see we have a border. Now, if you middle mouse click on any node in this chain, you'll see that we have a fairly large collection of groups now. It will show you exactly what groups you have, so, and how many components that belong to them. So this is very useful to keep track of what you're doing with your groups. Next, we want some way of placing our pieces. So if you take a look at a chessboard, you'll see that the rows and columns have letters and numbers, which allow players to specify where they want their piece. I should, as a disclaimer at this point, say I'm not a chess player, so if I get anything terribly wrong, I'm sorry. Now, we have our chessboard sitting in our Z direction, and we want to select groups of points where we're going to place our pieces. But first of all, I'm going to show you a really clever thing you can do with an attribute VOP that I just discovered the other day. So let's put down an attribute VOP. And open it up. Now the node that we want is called add point. And this creates a new point in the position that we give it. And we want to create a point in the center of each of our squares. So if we go back up to the top level, we want it to run over primitives and then take the position of each primitive and create a point at that position. Let's turn off our numbers and you can see that it's done it. So it's really simple and straightforward. Now we don't want our pieces to be placed anywhere in the board, we just want them to be on these 8x8 squares. So we use a group again, and we use group 2 is what we want. We obviously didn't name that correctly. So what we have here is our first group that we made, which is pointing in the upwards direction. And you can see we made that group before we made the edges, so it doesn't include the edge points. The only thing we didn't do was name it properly. So let's call this play space. And we'll need to go back down and update the group name. So now we have a point for every position that we might want one of our pieces to sit on. So the next thing we're going to do is create a group for every row and every column. So let's start with group. And we're going to use our group syntax here. So because each point is in the exact center of a square, and because each square sits exactly on the grid, then we should know the exact position of each point in each row and each column. So first of all, we want to work on points rather than primitives, and you'll see we're by default selecting all the points. And then we want to use our expression to select only the points where the x value is. So that will be minus 0.5, 1.5, 2.5, 3.5. So here we use @p for the position attribute, dot x, which is our x value, is equal to minus 3.5. And there we have our first column, which in chess would be the A column. So let's put in GA. The reason I'm not just calling it A is because when we get to the numbered rows, using a number as a group name is actually illegal. So we'll put the G in there to keep it legal. Now we have to do this 8 more times. Now, if there are any programmers watching this, you'll probably be very frustrated at this point that we can't just write a couple of loops to set all these up automatically. And in fact, we can using the Vex language, which would be relatively straightforward, but it's definitely for a later tutorial. So I'm going to set this up, but I'll also speed it up a bit so that you don't have to sit through the whole thing. Now that we have our rows and columns set up, we need some chess pieces. So I'm going to bring in some that I made earlier. So we want to merge these two files together and open up chess pieces. So here we have all the pieces, and if we go back to our chessboard, I'm going to hide the other objects because I don't need to see ghosts of the chess pieces sitting on my board, and I'm going to bring each piece in one at a time using an object merge node. What this does is allows you to bring other pieces of geometry into your network. It's really straightforward to use. So we click this symbol, which gives us a network to select, and then we can grab any of our other pieces of geometry. When you open it up, you can select any node within that geometry, and the last node for each of these is called out, which makes it much simpler to figure out which the final node is in our completed chess piece. So the first piece we want is the rook. So now we have that as part of our network, and we want to place that on the first square, which is A1. So I need some way to filter the A1 square, and ideally I want this to be something quite easy for the user to set up. So they just select an A and a 1 and the rook will automatically go to that square. So we're going to use another group combine node. And this time we're going to create a group, let's call it location, so that's where our piece is going to go. And the location is equal to our group 1, where it intersects with our group A. And here we have the correct point. And then we just need to use copy to points to place a rook on that point. That is definitely not what we want. In this case we can't filter copy to points by group, so we'll need to get rid of everything else, and here we can use the blast node. So go back to location and delete non-selected. So now we have our single rook sitting in the correct position. So it's going to take a little bit of time to set all these up, so I will speed that up for you again and be back with you in a minute. So now we have a board with all our chess pieces set up. At this point you might be wondering why we didn't just make lots of copies of the chess pieces and put their coordinates in, which would have been much simpler. The advantage of doing it this way is that we now have, for every single chess piece, we have a row and a column, and we can use that to determine the position of the chess piece. And this will allow us to set up a digital asset where we could just type in our rows and columns and have the chess pieces behave as we would expect. So I'm going to include a digital asset with this that does exactly that, which you can have a look at and play with. And we will very soon look at how to create your own digital assets. And through them be able to use Houdini in other software such as Maya and Unreal. Hope you've enjoyed this tutorial. Please subscribe and come back and see the next one.